Here we have a question on electrostatics. A spherical metal shell of inner radius r and outer radius 1.5 r has a charge of minus 4q. A point charge of plus 2q is also located outside the shell as shown above. Express all answers in terms of fundamental constants and the given values. So part A asks us to determine the charge on each surface of the spherical shell. Now, if we were to draw a Gaussian surface around the innermost shell of this metal, we will notice that the net electric field around this Gaussian surface is equal to 0, which in turn tells us that the charge contained inside the innermost shell must also be equal to 0. Moving on, if we were to again draw a Gaussian surface around the outermost shell, we figure out that the electric field that is generated or around this Gaussian surface is nothing but proportional to the charge contained, which is minus 4q. So the charge contained in the inner radius r is 0, while the charge or the total charge contained in the outer radius is equal to negative 4q. So that answers part 1 of subsection A. Moving on, sketch the electric field in regions 1, 2, and 3. We understand that inside a metal sphere or a metal shell, the total charge contained is 0. And since total charge contained is 0, the total field is also 0, which means there not be any electric field lines in the first region. Moving ahead, inside the second region as well, we consider this part, the entire second region, as highlighted here, as still a part that is inside the metal shell or the metal sphere. And as dictated above or as dictated before, we understand that the electric field lines are not present within a conductor, even though there is electric field strength that is produced outside the conductor on the surface. Hence, the electric field lines cannot be drawn in region 2 as well, since they do not exist. Moving on, in region 3, we understand that region 3 here is the external region, which has two charged bodies in close proximity. One of them is the metal shell shown here with a total charge of negative 4 capital Q, and another point charge at a small distance, which has a charge of plus 2Q. There are a few rules we need to remember while drawing the pattern of electric field lines. Electric field lines always originate from the positive charge and terminate at the negative charge. They do not form closed loops. Two electric field lines do never overlap, and they are always drawn perpendicular to the surface. Or if it is a point charge, they either all originate from a common point or terminate at the common point, depending on the polarity of the charge. Keeping these rules in mind, the electric field lines in the third region are drawn as follows. Moving on to the next part of the question, determine the electric field strength for the following radii. So let's answer part B. In part B, the first part asks us to find the electric field strength for the value R lesser than capital R. For the value of R being lesser than the value of capital R, we will use Gauss law. Gauss law in electrostatics states exactly this. It says that the net electric flux phi through a Gaussian surface is equal to 1 by epsilon naught times the net charge enclosed within the surface, where epsilon naught is the permittivity of the given region, which encloses the charges. And by the way, the region mentioned is supposed to be an isolated region which doesn't have any charge entering or escaping the system. Moving ahead, for the value of R being less than or equal to R, we can start with the equation. Flux phi is equal to Q by R square. Here the total charge enclosed is plus 2Q because it is a point charge. So the total charge Q net is 2Q, as we are ignoring the polarity, divided by epsilon naught. I know that flux also has another formula, which states that electric flux is equal to the strength of the electric field E, which is a vector, dot product with the area dA, along with cosine of theta. Since here we are assuming that the electric field lines are all perpendicular, the angle made between the field lines and the normal to the surface is 0. And since cosine 0 is 1, we are not going to involve cosine of theta in this. Moving ahead, I have flux E into dA, giving me E into the area. Since the charge is a point charge, the Gaussian surface I imagine around it is a spherical Gaussian surface. If there is a sphere of radius smaller, its surface area is 4 pi r square, giving me the expression area as 4 pi r square is equal to 2 into Q divided by epsilon naught. I can rewrite this expression as E is equal to 1 by 4 pi epsilon naught into 2 times Q divided by r square. Here I can assume 1 by 4 pi epsilon naught as the constant of proportionality K, and hence simplifying the equation further as K into 2 times capital Q divided by r square. This is the magnitude of the electric field strength, which is a vector. Moving on to part 2, I get to calculate part 2, where I'm sorry, let me write this. Part 2. Here we have the value of R, which is greater than R, but it is lesser than the value 1.5 R. Now here I understand that the electric field is 0 within a conductor, and hence the expression for electric field here in terms of its magnitude is also 0. Moving on to part 3, I have the value of R such that it is greater than 1.5 times the capital R. Let me correct this mistake. Small r is greater than the value 1.5 R. Now, in this case, I still use the Gaussian equation. Flux phi, which is equal to electric field E into area dA, is equal to Q net by epsilon naught. So here I can simplify it further. I can write electric field E into 4 pi r square is equivalent to the net charge. Here, when I consider the entire Gaussian surface, combining both the charges, minus 4Q and plus 2Q, the net charge contained is minus 2Q divided by epsilon naught. And when simplified further, I get E is equal to minus K into 2 times Q divided by R square. Moving on to the last part, that is part C of this question. We have determined the potential difference between infinity and the outside surface of the spherical shell. We understand that electric potential or electrostatic potential V and electric field E are related by an equation which is called the potential gradient, which is as follows. Electric field E is equal to minus the differential of potential with respect to the distance R. When rewritten and made the subject of the equation, V becomes equal to minus integral of electric field or the magnitude of electric field with respect to R. Here they have obviously straightforwardly mentioned in the question that the limits of R are going to be infinity to the outside of the spherical shell. The outside of the spherical shell is at a distance of 1.5 R. So my limits of integration are infinity to 1.5 times capital R. Substituting further, I get V is equal to minus integral under the limits infinity to 1.5 R electric field equation. And I know for this, the electric field equation is obtained under part 3 of the subsection B, which was minus K into 2Q divided by R square dr. Here the constants that are K and 2Q come outside the integration. The limits of integration are still applied for 1 by R square. And I know that, or we know that, the integral of 1 by R square is minus 1 by R. So minus 1 by R under the limits infinity to 1.5 times capital R. When simplified further, applying the definite integrals, we get the final equation for potential V to be minus 4 into Q into K divided by 3 times R. This is the expression for potential.